These are the notes for LT1 of the Applying Newton's Laws unit. So second unit, first target. And in this unit, we will eventually be taking Newton's 3 laws to a more in-depth mathematical level. But in order to do that, we have to set the stage and get some basic fundamentals. And that is what LT1 is going to do. So the first thing we have to be able to accomplish is to identify the magnitude, which means size, and direction of everyday forces. Okay, so identifying forces and knowing which direction they act. All right, so LT1, here we go. First thing we're going to do, just essentially a Google definition of force. And a force can be a lift, push, or pull on an object. So a lift, push, or pull. So if you're looking around wherever you're at right now, whether you're in a classroom, you're at your house, sitting outside, I don't know, wherever you are, like you should be able to look around and see, like, yes, there's forces in action. We don't necessarily see the force itself a lot of times, but we know it exists. If you're sitting in a chair right now, or on a bench, or on the ground, you know there's something keeping you stuck there. Okay, so Earth's acceleration, Earth's gravity, is pulling on your mass. So that force together is your weight. So every object, it could be a 2-atom molecule of oxygen that's going into your lungs right now. Every single object is acted upon by Earth's gravity and it's being directed downward. All right, so we're going to just draw something real simple because you know that it has to be simple, and I can still mess it up, but either way. Let's just say that this is a table, and sitting on this table, we have, it's morning for me, so nice mug of coffee. All right, maybe you are anti-coffee, it's hot chocolate. And so we've got this cup of hot chocolate, and it's going to stay sitting on that table for 2 reasons, a couple. First one, gravity's doing its thing. So we would know that the weight of the mug, which is a force, okay, there's one of our forces, so I'll highlight that, is directed downwards. Okay, weight is always straight down because it's originating, I should say gravity is originating in the core of the Earth. So the weight is straight down. Now, your coffee, hot chocolate, whatever that might be, is not crashing to the ground. And that's because the table is able to exert a force. And that force is an upward force, and it will be exactly equal and opposite. And that is called 2 different things that mean the same thing. A support force, which probably makes perfect sense, but it's also called a normal force because it acts perpendicular to the object. It's a geometry term. All right, so we'll call it both things. This weight is sometimes abbreviated F-grav to show that it's gravity doing it. This force is often called F, and then the subscript is norm, okay, for a normal force. So there's another type of force that we have to be able to identify. So it could be, like I said, you sit in the chair, you sitting on the ground pushing up. If you sit on a swing, the swing pushes up. If you sit on a ledge, the ledge pushes up. All right, so that's a support force, always acts upward against the object. Now something to note about these forces, I've been paying a lot of attention to this direction. We just don't point at something and go, ooh, wait, ooh, support force. These are vector quantities. Okay, vector quantity. A vector means that size matters and direction, so which way it's going. Remember that whole distance versus displacement thing from the last unit. Distance was not vector, it's called scalar. It's just how far did you go. We don't care which way you went, just how far did you go. But displacement was where did you end up. So did you end up 3 kilometers north? As soon as you put a direction on something, that makes it a vector quantity. A push is very different from a pull. Okay, maybe you shoot a bow, shoot archery. You know that pulling on the bowstring would be very different than pushing on the bowstring. Okay, so vector quantities, that's what we deal with in this unit. Speaking of units, the unit of measurement for a force, we don't just say it's 100 forces or anything weird like that. It's 100 newtons. Okay, so this newton is the unit, obviously named after Sir Isaac there. So we might say that you pushed on the door with 25 newtons of force, something like that. All right, so you'll just see that as a capital N. So far, 2 types of forces. We're going to have 5, kind of 6 here in this target. The next one, if you've ever got a scrape, you know well about friction. Okay? So friction, there's a couple things here. First thing, there has to be direct contact. If you play sports or you are just graceful and have wiped out, you know that when you take a tumble across carpet or dirt or whatever, a lot of times you get scuffs, you get scrapes, you get strawberries. All right? You know there's direct contact there in order for that to happen. And that friction always opposes motion. So if you go diving into home, that dirt is going to slow you down. It always acts opposite. You go sliding down a railing, which we're going to draw here in a second. That friction isn't going to help you go faster. You don't go faster because of the friction. All right, so think about friction always slows you down, always slows an object down. So here's my next attempt at drawing something. When you walk to physical science, most of you go through the commons. We call it the commons. You have to go down those steps at the top of the senior hall, and there's a railing on those steps. So let's see if I can not mess this up too bad. So here's a railing, and so far so good here. And here comes somebody. Now this is where it's going to go to heck, but here's somebody sliding down the railing. So there's their other foot, and here's their happy face and their arms. It looks like they only have 3 fingers on each hand, but that's okay. And here they go down the railing. Okay, coming to physical science. I'm sure they're very, very excited. And we know that their motion is going to be this way. That is not a force. I'm not going to highlight that. That's due to inertia. Newton's first law. We'll deal with it next target. But they don't crash through the railing, through that metal. And the reason for that is there's an upward force that we've already talked about. That is the normal force. That is pushing up on them, preventing them from collapsing down. Because we know that Earth's gravity is not pulling them at that angle. Earth's gravity is trying to suck them to the core of the Earth. So Earth's gravity, which we're just going to say F grav, or their weight, is straight down. And friction is trying to slow them down. So it will work at the angle against them. So friction is our new force here. And we would write that F-R-I-C-T. So the subscript is frict. So friction is our third force. Now another type of friction that we deal with is air drag. And it can be called air drag or resistance. Doesn't matter. Same idea. We all know about this idea of air drag. And, just the kind of the boring example because we've already used it, but to keep this simple, think about a parachuter. Okay, so here's our parachuter coming back. And here they are. And we've got the chute strapped to them. We know that if you jump out of an airplane, it's your weight, it's the force of gravity, or your weight that's coming straight down. And air drag is going to push up to slow you down. And it doesn't always have to act up. If you're riding a bike, you know that the faster you pedal, the more you can feel the air pushing against you. If you wave your hand in the air right now, and I know it looks really cool, but the faster you wave your hand, the more you can feel the air. So that air drag is always working against the motion of your hand. Okay, so air drag is just another type of friction. And the last thing our last force we're gonna worry about here today is called the force of tension. It's not the type of tension of, I've got a test today. Not that kind of tension. It's the tension in a rope, a cable, a chain, okay, something like that. So if you have ever walked a dog, right, and you've walked a dog that maybe doesn't have real good manners like mine, and she pulls hard on the leash, okay, there's tension in the leash. We can tell that there's a force there. We could say right here, even in this drawing, those cords or whatever it is that are holding the chute to this person, that is the force of tension. F10s is how we do that. Okay, so that would be a force. Maybe we've got a picture. That's a nail, not a picture. But maybe there's a picture hanging on your wall somewhere that has like little strings to it. Some little crafty thing. All right, so here's a picture. and it's of you because you're awesome. All right, so there you go. That does not hopefully look like you. But, okay, if there's a picture and it's hanging from a nail, well, the force of tension would be pulling up on each side of that. So the force of tension would be there. Because we know that the weight, the force of gravity, is pulling down. If you've ever buried a four-wheeler, a quad, right, your dirt bike, a side-by-side, I know that I've possibly gotten my dad's Ranger stuck a couple times, and he's always super impressed with me. And so when you get hauled out, there's tension in that rope. There's tension because you're often in trouble too, but there's also tension in the rope that's pulling you out of there. All right, that acts along the rope or the chain, whatever it might be. So let me highlight our last force. We've got 1, 2, 3, 4, 5, which was the goal. And if you understand this, you are ready for LT1. Good luck.